Hey guys, welcome back to my channel. I'm back with another video in the mathematical modeling video series, and today we're going to be doing arguably the most important thing when it comes to mathematical modeling. So like I mentioned in the previous videos, we make models with the intention of solving specific problems, and the last step in solving those problems once we've made the model is to come up with the right conclusions and the best recommendations to solve the problem. So when we talk about diseases, there are terms like reproduction number and various other terms like that, which can be derived from the mathematical model. And all of that arises from this very important concept that we're going to be learning today. So for the next couple of weeks, we're going to be taking a bit of a break from making new models, but we're going to be discussing concepts that will help us come up with recommendations from the models that we've already created. Okay, so let's get started with stability analysis. So what is stability analysis? And now to understand that, we first have to understand what a dynamical system is. So a dynamical system can be essentially thought of as a system where the state is time varying and it follows a fixed set of rules. So what does this exactly mean? So if you think about our SI model, right, which we discussed in the previous videos. So the S comma I, so basically the value of S and I at any instant of time is nothing but the state of that system, right? The number of susceptible people and the number of infected people together give you the state of the system. And it is time varying because with every instant of time, the S and I state, like S and I together, the state of the system keeps varying. But at the same time, it follows a fixed rule. And what is that rule? The rule was the differential equation that ds by dt is equal to minus beta si. So S, the susceptible population, follows this rule, which is essentially given by this differential equation. Now, dynamical systems can be either continuous time or discrete time. Like I already mentioned, so far every model that we've discussed is a continuous time differential equation, and therefore it's a continuous time dynamical system as well. So what are the types of dynamical systems? So dynamical systems can be linear or non-linear, and this is extremely important to understand, and it's extremely important to be able to differentiate between linear and non-linear dynamical systems. So linear dynamical systems, very simply put, have no non-linear terms in any of their equations. So what do I mean by that? I'll explain that very shortly. And non-linear dynamical systems obviously have at least one non-linear term involved in the system equations. So to give you a super simple example, so ds by dt is equal to minus beta s into I. So, and that's one equation, and di by dt is equal to plus beta s into I. Now, the state variables of this model are nothing but s and I, right? So S and I are nothing but the state variables of this model. Now we have a term in ds by dt which is S into I. So that makes it a non-linear term, right? Because if you have two state variables and you have a product of them, that becomes a non-linear term. And therefore the SI model is in fact a non-linear dynamical system. So what would be an example of a linear dynamical system? So a good example would be something like, let's say dx by dt is equal to 3x plus 3y plus 5, and dy by dt is equal to y minus 1, where x comma y are the state variables. So something like this would be linear because the only terms that have x and y have only x and or only y. They don't have a product of x and y. They don't have an x square term. They don't have an x cube term. They don't have an x square into y term, nothing like that. At the same time, if this equation, if even one of these two equations had x square, let's say, now the whole system would become a non-linear system just because of this one term right here. So it's important to understand the difference between linear and non-linear dynamical systems. Now, once we've understood the difference between them, we can go ahead and start with the main aspect of this video series, which is equilibrium points. So what does an equilibrium point mean in a dynamical system? So in general, you can think of an equilibrium point as basically a point where the state of the system does not change. And due to this, equilibrium points are also called fixed points because the state at that particular point will be fixed. It does not change. Now, when it comes to differential equations, equilibrium point can be thought of as the point at which the rate of change is zero, where this is a vector. So what I mean by that is x would be s comma I if we are talking about the SI model. So what this would translate to is that ds by dt is equal to 0 and di by dt is equal to 0. Right? So this is a system of differential equations. So what's the difference between a differential equation and a system of differential equation? A differential equation would just have one variable involved in it, the rate of change of one variable. A system of differential equations would essentially have the rate of change of many variables involved in it in different equations, and those equations together are called or is called the system of differential equations. So S and I together form a particular system. So when it comes to differential equations, the rate of change being equal to 0 is basically the solution of that would basically give me a fixed point. So like I've mentioned in the definition here, if you have a system of differential equations, we set all the differential equations equal to 0 and then solve those equations simultaneously. So what does that mean? We'll take an example and discuss now. So now we've discussed the logistic population model before, right? So that's dp by dt is equal to sum r times p into 1 minus p by k. This is the logistic growth model which we had discussed before. Now this is a differential equation, correct? And this describes the population growth model. So let's say I wanted to find the equilibrium points of this differential equation or this, this particular system, whatever this describes, which is the population growth. If I wanted to find the equilibrium points, I would just equate it to 0 because dp by dt equal to 0 gives me the fixed points or the equilibrium points. So now once I do that, I essentially have to solve it. So the 2 points I get are p is equal to 0 and p is equal to k. These are the 2 points I get. So there are 2 equilibrium points. So the logistic population model has 2 equilibrium points. So what do equilibrium points signify? Why should I talk about equilibrium points? That is an important question. So equilibrium points are the points around which we discuss stability. So what does stability mean? Which is arguably the most important question. When it comes to any dynamical system, understanding stability and being able to comment about stability is extremely important. So if I consider I have a pen, right? I have a pen and I'm balancing it on my hand like this, right? So currently, because I'm holding it with my other hand, it's stable, it's not moving. But the moment I left it, it would fall. So this inherent point, this point, without me holding it, this point would be an unstable point for this whole system, right? For the pen and my hand together, if I'm considering this as one system, that's an unstable point because if I even cause a small variation to, maybe I'm able to balance it like this, okay, exactly at this point, it's possible. But the moment I introduce any small change, like I push the pen a little bit to the left or the right, it will never return to the original point. It will always fall down. So it's unstable. So stability in one sense can be thought of as if at the equilibrium point, I introduce a small variation. So let's say I change the state of the system by a small amount. If in some time the state of the system returns back to the original point, it is stable. If that does not happen, but if it goes into some entirely different state and never returns back to the original state, then it's unstable. That's the way in which you can visualize stability. Now, on the other hand, okay, so let's say I had this is a nail, let's say, and I had a picture hanging on the wall like this. Okay, this is a nail. So I'm just going to put an X mark here. Maybe I'll use some other color. So this is a nail and this is a picture hanging on a wall. So this, let's say this is the wall. Now if I push the picture like that a bit, obviously it will start rotating around this point, right? It will go back and forth, back and forth, back and forth, but with time eventually it will return to this exact same position. So this point in this particular system with the picture and the nail on the wall, this system together, this point can be thought of as a stable point. Why? Because when I introduce a small disturbance to this initial state, so this is the initial state, this picture being exactly hung like that on the wall is the initial state. Now I introduce a small disturbance, which is me pushing the picture a bit to the left or right, doesn't matter. So now it will start rotating to and fro, to and fro, to and fro, and it will eventually come back to that exact same initial state. So this can be thought of as a stable equilibrium point. But now, before we discuss it, let's talk a bit more about planar systems. I will get to the exact definition of stability very soon. I just wanted to give you the notion and the idea of stability. So what are planar systems? Now, planar systems are nothing but linear systems which have two variables. If there's, so essentially you can think of it as the real plane, so the x and y axis. So if you have the x and y axis together, it's a 2D thing, it's a plane, right? That's the plane, the real plane. So the most general planar system can be denoted like this. So here x dash and y dash denote dx by dt and dy by dt, and I'll be using this dash notation very often in the coming slides, so which is why I'm just giving you an idea of what it means. So any planar system can be represented in a matrix or a vector form. So this is the matrix representation of 1. So let's call this 1. Cool. So basically we define this matrix A as A, B, C and D, which are nothing but the coefficients of x dash and y dash, and we define x as the vector x and y. So x is nothing but the state, right? The state of the system. Now, for those of you who have done differential equations and solving a system of differential equations, know how to find the solution of this equation x dash equal to ax for this equation. If you have not solved differential equations before, I highly recommend that you just look it up so that you can understand how I arrived at this particular solution. If not, if you feel that it's not really important for you to learn how to solve differential equations and you just want to take my word for it for now, that's okay, but I highly recommend that you do learn how to solve it, because otherwise it's going to be a bit difficult in general. So now the solution of this planar system can be given as alpha times e power lambda 1t into v1 plus beta e power lambda 2 into v2. So here lambda 1 and lambda 2 are called eigenvalues of, so lambda 1 comma lambda 2 are eigenvalues of A, and v1 and v2 are the corresponding eigenvectors. So again, for those of you who don't know how to find eigenvalues and eigenvectors, you will need to learn how to do that, and it's super important that you learn that. That doesn't take too long. There are plenty of videos online that you can watch to understand this. So this and alpha comma beta are essentially just real numbers. So this is the solution to the planar equation. Okay, I hope this is clear, the solution curve and what lambda 1 comma lambda 2 and alpha comma beta represent, and what v1 and v2 represent as well. So now that we know what a planar system looks like, I'll introduce the concept of stability officially. So stability essentially stability can be thought of as the notion where it's the notion where A small change about the equilibrium point causes, okay, actually not causes, with time causes the system to return to the original state. So basically a small change about the equilibrium point with time, right? So in time, even if I introduce a small change about the equilibrium point, the state of the system should return to the original state from where it started. If this happens, then we can say that the system is stable. If not, we say the system is unstable about that equilibrium point. So it's important to understand that stability is often discussed about the equilibrium point, and the equilibrium point, so saying a system is stable only makes sense if you say a system is stable about this equilibrium point, or a system is unstable about this equilibrium point. So that's what you need to understand, that we discuss stability most often with respect to a particular point. Saying a system is stable in general would not make a lot of sense, right? Because you are talking about introducing many changes or disturbances to the system only at those specific equilibrium points. Cool. So now that I've introduced the notion of stability, we will now look at why it's important for us to why I discussed that solution and why it's written in that way, the e power lambda 1 t, e power lambda 2 t, why that's important. We'll discuss that right now. So basically, if we have a one-dimensional differential equation, right, and so let's say it's x dash equal to ax, where a belongs to the real numbers, is just any real number, doesn't matter. So the solution to this is actually x of t is equal to k into e power at, where k is an arbitrary constant, and if we know what the value of x of 0 is, then k is nothing but x of 0. Now the equilibrium point of this x dash equal to ax is nothing but the point x is equal to 0. Now if you're talking about the stability at the point x equal to 0, how do we think about that? How do I conclude whether x is equal to 0 is a stable equilibrium point, or if it's an unstable equilibrium point, or if the system is stable about the equilibrium point x equal to 0? How do I comment about that? That's what we're going to see right now. Now, if let's say I cause some small disturbance, so basically x equal to, so from x equal to 0, I'm moving to x equal to plus or minus epsilon, where epsilon is sorry, that's not epsilon, where epsilon belongs to some real number and it's a small value. Right, so what happens? So if you look at the solution curve, so as I'm moving away from x, okay, so let's draw the graph. Maybe that will help you guys understand better. So the exponential curve is actually an increasing curve. So at 0, let's say this is k, and so this is the exponential curve if a greater than 0. This is the most important part. I'm assuming that a is here, this a in this equation is a positive value. And now why is that important? Because if a is increasing, if a is a positive value, then the exponential curve e power at will be an increasing exponential curve. Otherwise, if a is less than 0, it will be a decaying exponential curve, which is extremely important. And I will discuss that if a is less than 0 in the next slide. So for now, let's assume a is greater than 0. So x is equal to 0 is this point. This is x equal to 0. and this is the time axis. So this is x equal to 0, it's over here. So if I'm moving towards the right, so if I'm going to plus epsilon, so let's say epsilon is somewhere here, what is going to happen to my system as t tends to infinity? Let's just follow the solution curve. So the solution curve will essentially take me further and further away from the starting point, right? And why is that? That's because e power at tends to infinity. As t tends to infinity, under this condition, if a is greater than 0, e power at tends to infinity as t tends to infinity. On the other hand, if a less than 0, e power at tends to 0 as t tends to infinity. So that would essentially mean that if we're starting from k or something like that, like it's going to be a decaying exponential. No, that's probably wrong. Something like this. But the thing to remember is x of t, which is some k times e power at. Initially we are saying that x of 0 is, let's say we're starting from x of 0 is, it doesn't matter, right? We're starting from x is equal to 0. That's what we were saying. So we are saying that we're starting from x equal to 0 is the equilibrium point. And as t tends to infinity, x of t will also tend to 0 if a is less than 0. That is the important thing to realize here. So if a is less than 0, the state, it returns to the original state from which we were, this is the equilibrium point, but it returns to the original state. If not, if a is actually a positive value, we keep going further and further away from the state. So what is important to realize here is this. A is in fact nothing but the eigenvalue of this system. So lambda is lambda, which is equal to a. So a is the eigenvalue of this system 1. So that means the important inference from this whole discussion, which will help us in the next slide, is that if lambda is a positive value, then the system tends to be unstable about that equilibrium point. If lambda is negative, so this is lambda, if lambda is negative, the system or that equilibrium point is a stable equilibrium point. So lambda positive, unstable, lambda negative, stable. Cool. Now we come back to our planar equilibrium points. So we have two eigenvalues, lambda 1, lambda 2. So again, lambda 1 equal to lambda 2 equal to lambda. So lambda 1 comma 2 is equal to alpha plus or minus I beta. Correct? So now if we have, so there are three possible cases with our eigenvalues. Like one, we have two distinct eigenvalues, or you have two distinct, or you have complex eigenvalues, or you have repeated eigenvalues. Why? Because when you have a planar system, the eigenvalues actually arise from a quadratic equation. So when you have x square plus ax plus b equal to 0, and let's say the roots of this are lambda 1 comma lambda 2, these are the three possibilities, right? 1, 2 and 3. So now if both are positive, so lambda 1 greater than 0, lambda 2 greater than 0, that means that both e power lambda 1 t term and e power lambda 2 t term both will tend to infinity as time is progressing. So therefore we can say that this will be unstable. Now both negative, that means e power lambda 1 t tends to 0, e power lambda 2 t tends to 0. Therefore we can say this is stable. This again, if one is positive, one is negative, that is still an unstable combination. Why? Because if one is, if one of the parts of the solution is tending to infinity, you can think of it this way. It's not the exact way of thinking about it, but infinity plus 0 you can think of it as infinity. It's essentially the solution curve will be tending away from the origin. So again, this will be unstable. Now repeated eigenvalues. If both are lambda, what is the scenario? Again, it depends on the sign of lambda. Now, if lambda greater than 0, we can say it is unstable. If lambda less than 0, it is stable. Simple enough. Based on our discussions from the one-dimensional equation, I've just extended it to 2 dimensions. And now this can be extended to n dimensions, which I will discuss very soon. Now the most important case is complex eigenvalues. And why am I saying it's most important? Because in real life, almost every real life system ends up giving you complex eigenvalues. And when we discuss the SI model and stuff like that, you will see why I am saying this. Anyway, for now we have alpha plus or minus I beta. So here again, when you have e power alpha plus I beta, so it's just e power alpha, e power I beta. So the real component is essentially this, right? So we don't care about this term. You just have to look at this. And the whole thing will be, okay. So essentially you will have to see again. So if alpha is greater than 0, we can say unstable. And if alpha is less than 0, we can say stable. Now this is just a very brief introduction. Each of these cases of eigenvalues have a special name to the curve. Like for example, there is a curve called this inward spiral, the outward spiral. There's something called a focus. There's something called a circle. And we will deal with all these terms later. Okay. I just wanted to introduce the concept and the way in which you can think about stability based on eigenvalues. And I hope that's amply clear, which is why I discussed the one-dimensional case to give you the idea. And I extended that to the 2-dimensional case. So now just to summarize, essentially we can say in a 1D case, simply based on eigenvalue, if lambda greater than 0, it's unstable, and lambda less than 0, stable. In a 2D case, it depends again on, so if lambda 1 and lambda 2 positive, it's unstable. Lambda 1 comma lambda 2 both negative, it's stable. Lambda 1 equal to lambda 2 negative, stable. Lambda 1 equal to lambda 2 positive, unstable. And then of course there's the complex roots. Complex roots, which we haven't discussed entirely. We will discuss that in the next video. So in this video, I introduced the concept of the notion or the concept of stability and how to discuss it for a 1D case and how to think of it in the 2D case. We will discuss it in detail in the next video and also start discussing about stability analysis for a non-linear dynamical system. Like the SI model is a non-linear system. Everything we've dealt with till now have been linear systems, like planar 2D linear systems. So how do we deal with this for non-linear systems? We will do that in the next video. Anyway, thank you so much for watching. And if you have any doubts, make sure you drop a comment. And I understand that it might be slightly confusing right now because we just introduced stability, but after the next video, most of your questions will be cleared. And in the next to next week, I will do an entire summary of the whole stability analysis, and we'll discuss stability for all the systems we've talked about till now, the SI model, the SIR model, and the population growth models, everything. We will discuss stability for all of them. As always, thank you so much for watching, and I'll catch you next week with the continuation of stability analysis.